Welcome back. In this session, we're going to talk about Maxwell's equations. But fear not, you've already learned 3 of them, and they're the harder ones. During our discussion of electric fields, you learned about Gauss's law, which states that a charge will produce an electric field. From the electric field, you can calculate potential and then the capacitance of different configurations. During our discussion of magnetic fields, you learned about Ampere's law, which states that a current will produce a magnetic field, and you learned about Faraday's law of electromagnetic induction, which states that a time-varying magnetic flux will produce a potential, also known as an electromotive force, or EMF, in a loop. We showed how to apply Ampere's law and Faraday's law to calculate the inductance of different configurations. Gauss's law, Ampere's law, and Faraday's law are the first 3 of the 4 equations that have come to be known as Maxwell's equations, named for James Clerk Maxwell. For historical context, it must be noted that when Maxwell published a treatise on electricity and magnetism in 1873, he included over 20 equations. Some years later, Oliver Heaviside studied Maxwell's work and synthesized these equations into this set of 4 that we know, love, and use to this day. Thus, it is more accurate to call these Heaviside's equations, though there is no question that much of the foundations were laid by Maxwell. The only equation we have not yet discussed is the 4th one, which is Gauss's law for magnetic field, which simply states that the total outward magnetic flux through any closed surface is 0. Another way of stating it is that there are no magnetic flow sources, and that magnetic flux lines always close on themselves. This equation completes the quartet, but the main heavy lifting for most of the analysis work we will be doing is performed by the first 3, which you have already learned. Now you've learned Maxwell's equations, or Heaviside's version of them, and it wasn't so scary, was it? These equations really do form the basis of our understanding of electromagnetics. So let's plunge in a little deeper and see what more they tell us. Up until this point, I have been telling you that I prefer the integral forms of these equations because I think they provide a more intuitive description of the physics of how fields are generated by charges and currents. For this next discussion, we will turn our attention to the differential forms because they provide some additional interesting insights to show how the energy generated by these fields will propagate as electromagnetic waves. If we are far away from any charge and current sources, we can set the charge density and current density terms to 0 in the first 2 equations. We can also replace the magnetic flux density B in the 3rd equation with the permeability mu times the magnetic field intensity H. Now we have our set of equations for the special case of a source-free medium. Before we plunge too deeply into the math, we can see that the 2nd and 3rd equations provide some intuitive insight due to their symmetric relationship, as shown in the following simplified illustration. Per the 2nd equation, a time-varying electric field will be accompanied by a magnetic field that curls around it. The magnetic field must also be time-varying, which, per the 3rd equation, will be accompanied by a time-varying electric field that curls around it, which will in turn be accompanied by another time-varying magnetic field, and so on and so on. And this is how the energy from these fields propagates through space as electromagnetic waves. Strictly speaking, the actual physics of the behavior of electric and magnetic fields is much more complex than this. It gets down to the quantum level, and it has been studied at great length by many great scientific minds over the years. As such, it is beyond the scope of what I plan to cover in this video, but this simple illustration conveys the general idea sufficiently to allow us to continue the discussion. Personally, I find it fascinating and necessary to note that while formulating his theories, Maxwell introduced the concept of the displacement current in a dielectric because the math literally did not add up without it. Its existence was eventually verified with laboratory measurements, and it has long since been an essential ingredient in our understanding of electromagnetics. It is one example of many in which a mathematical and theoretical construct led to a significant discovery. We're going to plunge a bit deeper into the math here, but stick with me because we will arrive at some results that will provide essential tools that we will use going forward, and we'll see another example of math and theory leading the way. Returning to our equations for the special case of a source-free medium, the second and third equations are in terms of both H and E. We'd like to rearrange them to get one equation completely in terms of E and another completely in terms of H. Starting with the third equation, we take the curl of both sides, and the second equation allows us to replace the curl of H with epsilon dE dt. And the right side of the equation equals minus mu epsilon times the second time derivative of E. Now we make use of a vector identity that states that for any vector field A, the curl of A equals the gradient of the divergence of A minus the vector Laplacian, or del squared, of A. I'll show you the proof of this identity in a separate session that will provide a review of some vector calculus fundamentals. When we apply this to the electric field, our first equation tells us that the divergence of E equals 0. The first term disappears, and we are left with the curl of E equals minus del squared of E, giving us the second order differential equation that states that del squared of E minus mu epsilon times the second time derivative of E equals 0. Following the same approach, we arrive at a similar equation for H. Now we have two second-order differential equations for electric and magnetic fields. In this form, these are three-dimensional equations operating on all three vector components of E and H, which would make for a rather complicated analysis. As is often the case with mathematics, we can make a few assumptions that will greatly simplify the analysis while still providing valuable insights into the basic physics. When we are sufficiently far from a source of electromagnetic energy, it looks like a point source, and the energy propagates outward as an expanding spherical wave. When we are farther still from the source and are looking at a very small portion of the spherical wavefront, we can approximate it as a uniform plane wave, which is much simpler to analyze. In what follows, we will look at a uniform plane wave in the xy plane, propagating in the plus z direction, and having an electric field with only a component pointing in the x direction that we will call E sub x. This allows us to simplify our three-dimensional differential equation for electric field by setting all of the y and z terms to 0. We can simplify further by also setting the spatial derivative terms in the y and z directions to 0. This gives us this much simpler differential equation in a single dimension for the component E sub x. The general solution of E sub x as a function of position on the z-axis and time t is given by the amplitude E naught multiplied by the exponential of j times omega t minus beta z, where omega is the angular temporal frequency in radians per second, and it equals 2 pi times the temporal frequency f, because there are 2 pi radians in a full cycle. Because the frequency is the reciprocal of the temporal period t, we can also write it as omega equals 2 pi over t. Beta is called the wave number, and it is in units of radians per meter. The wave number is also sometimes shown as k, but I will be using beta going forward. The wave number is defined as 2 pi divided by the wavelength lambda. We can see a parallel relationship between omega and beta, and between the temporal period t and the wavelength. Plugging our general solution into our differential equation, we see that E naught times the exponential term equaling 0 is not an interesting or useful solution. So we factor it out, set the remaining terms equal to 0, and see that the wave number beta equals omega times the square root of mu epsilon. We will come back to this shortly. Taking the real part of our general solution, we get E naught times the cosine of omega t minus beta z. Here is a notional graph of this function at time t equals 0. If we advance in time by 1/4 cycle, which is to say that omega delta t equals pi over 2 radians, then the entire waveform will advance in space by 1/4 cycle as well, which is to say that beta delta z also equals pi over 2 radians. If we advance in time by another half cycle, which means that omega delta t equals pi radians, then the entire waveform will advance in space by another half cycle, which means that beta delta z also equals pi radians. If we advance in time by a full cycle, where omega delta t equals 2 pi radians, then the entire waveform will advance in space by a full cycle, where beta delta z also equals 2 pi radians. The delta z corresponding to a full cycle is known as the wavelength lambda. Setting delta z equal to lambda, we see that the wave number beta equals 2 pi over lambda. Clearly, the wavelength in the spatial domain is the direct counterpart to the period t in the time domain. The general case is that omega delta t always equals beta delta z, or that omega delta t minus beta delta z equals 0. Rearranging terms, we see that delta z over delta t equals omega over beta. Taking the limit as delta t approaches 0, we get that the time derivative of z, which is by definition the speed of propagation of the wave along the z-axis, equals omega divided by beta. Given the relationship between omega and beta, we can also write that the speed of propagation equals the wavelength divided by the temporal period, or the wavelength multiplied by the temporal frequency. Going back to our expression for beta, we can rearrange terms to see that omega over beta, the speed of propagation, equals 1 over the square root of mu epsilon. In free space, this equals 1 over the square root of mu naught times epsilon naught. Remember that mu naught equals approximately 4 pi times 10 to the minus 7 henries per meter, and epsilon naught equals approximately 1 over 36 pi times 10 to the minus 9 farads per meter. Before we look at the numbers, let's look at the units. Inductive reactance in ohms is equal to inductance in henries multiplied by j omega, or j2 pi f, with f in hertz, or 1 over seconds. Thus, a henry is equivalent to an ohm second. Capacitive reactance in ohms is equal to 1 over j omega times the capacitance in farads, or 1 over j2 pi fc. Thus, a farad is equivalent to a second per ohm. When we multiply mu naught by epsilon naught, the units are Henry farads per square meter. A Henry farad reduces to square seconds. Now we multiply everything through, numbers and units, take the square root and the reciprocal, and we get 3 times 10 to the 8th meters per second, or 300,000 kilometers per second, or 186,000 miles per second. Sounds a bit like the speed of light in free space, doesn't it? Because it is. Strictly speaking, the exact value of the speed of light in free space or vacuum, designated by c, is 299,792,458 meters per second. Mu naught has been measured experimentally to the value shown here. Our approximation of 4 pi times 10 to the minus 7 henries per meter agrees with this experimental value out to 9 significant digits, or to less than 1 part in a billion. Epsilon naught has been measured experimentally to the value shown here. Our approximation of 1 over 36 pi times 10 to the minus 9 farads per meter agrees with the measured value to within 0.2%. And our approximation for the speed of light agrees with the exact value to within less than 0.1%. If high precision is needed, it is good to know these exact numbers, but for most purposes, the approximations are sufficient to facilitate quicker calculations, as we will see momentarily. but it's always good to keep in mind that they are indeed approximations and not exact values. Let's return to the relationship between speed of propagation and the ratio of omega over beta, now applying it to the speed of light in free space. As stated earlier, this is equivalent to saying that the speed equals the wavelength divided by the temporal period, or that it equals the wavelength multiplied by the temporal frequency. This is a very important relationship to remember, and we will be making ample use of it. We can rearrange it to show that the wavelength equals the speed of propagation divided by the temporal frequency. Using our approximate value for c of 3 × 10⁸ meters per second, we can temporarily rewrite it as 300 megameters per second to arrive at this handy expression that shows that the wavelength in meters approximately equals 300 divided by the frequency in megahertz. RF engineers dealing more in the gigahertz range like to use this form, stating that the wavelength equals 0.3 divided by the frequency in gigahertz. The expressions are clearly identical and can be applied to their respective frequency ranges as needed. And clearly, the approximate value for the speed of light facilitates a much quicker calculation than using the exact value. This relationship between wavelength and frequency is another thing worth committing to memory because we'll be using it all the time. It is especially useful at frequencies for which any circuit element is a significant fraction of a wavelength, when it can behave as a transmission line or an antenna. For example, at 10 MHz, the wavelength is 30 meters, and a tenth of a wavelength is 3 meters, or about 10 feet. This is right in the range of the length of cables in a typical setup. And 10 MHz is not a terribly high frequency in the grand scheme of things, and the effects only get more pronounced as the frequency increases. As you may have guessed, we will be discussing this further in future sessions. The preceding discussion was all about the electric field and the solution for its second-order differential equation. Because the differential equation for the magnetic field has the same form, its general solution will also have the same form as the electric field solution. All that remains is to sort out the direction and the relative magnitude. Let's go back to the original equation stating that the curl of the electric field equals negative mu multiplied by the time derivative of the magnetic field. For our plain electromagnetic wave, we defined the electric field to have only a component in the x direction called E sub x. Thus, the curl of E will have a vector component only in the y direction with a magnitude equal to the derivative of E sub x with respect to z, which equals minus j beta times E naught times the exponential term. Looking at the right side of the curl equation and our general solution for h, we see that the time derivative of h equals j omega h, bringing the right side to minus j omega mu h. Comparing this to the expression we just derived for the curl of E, h clearly has only a component in the y direction. Canceling like terms and rearranging the remaining terms shows that the ratio of the electric and magnetic field amplitudes equals omega mu over beta. Remember that omega over beta equals 1 over the square root of mu epsilon, and the resulting expression is the square root of mu over epsilon. Given that electric field is in units of volts per meter, and magnetic field is in units of amperes per meter, this is defined as the characteristic impedance of the medium, designated by the Greek letter eta, in units of ohms. In free space, this equals the square root of mu naught over epsilon naught. From our earlier discussion about units, we see that a Henry per farad is equivalent to a square ohm. Thus, the characteristic impedance of free space is approximately equal to 120 pi ohms, or approximately 377 ohms. These are a couple more numbers worth committing to memory because you'll see them again. For a uniform plane wave, the magnetic field vector will be orthogonal to the electric field vector, and it will have an amplitude equal to the electric field amplitude divided by the characteristic impedance of the medium. In free space or vacuum, That will be approximately 120 pi, or 377 ohms. The cross product of the E and H vectors gives the Poynting vector, which is indeed named after a dude named Poynting, John Henry Poynting to be exact, who discovered and derived it in 1884. So yes, electromagnetics history provided a ready-made pun for us here, because the Poynting vector does indeed point in the direction of propagation, which is orthogonal to both of the E and H vectors. In this example, with E in the plus x direction and H in the plus y direction, the Poynting vector points in the plus z direction. Its magnitude is the product of the magnitudes of E and H, which gives the power density of the propagating wave in watts per square meter. By the way, this is that other example of math and theory leading the way that I mentioned earlier. Maxwell proposed the existence of electromagnetic waves because the math said they should exist. And because the speed of propagation in free space predicted by the wave equations coincided with the speed of light, Maxwell correctly concluded that light itself is an electromagnetic wave. Maxwell's predictions were later confirmed by Heinrich Hertz through his experiments with radio waves, and we say his name every time we talk about the frequency of those waves. Theory and experiment, always two sides of the same coin. This session was clearly highly theoretical, but we arrived at some valuable analytical tools that we will be using a lot going forward. In addition to showing that electromagnetic energy propagates through space at the speed of light, we showed that the wavelength of those resulting waves equals the speed of propagation divided by the temporal frequency, which leads to these equivalent forms that provide a quick conversion of frequency to wavelength. The characteristic impedance of the medium is given by the square root of the permeability divided by the permittivity. In free space, this equals approximately 120 pi, or 377 ohms. In the simplifying case of a uniform plane wave far from any sources, the electric field and magnetic field vectors are orthogonal to each other, and the wave propagates in the direction normal to the plane given by the Poynting vector. The magnitude of the Poynting vector gives the power density of the propagating wave in watts per square meter. All very useful tools provided by the math and verified by experiment. We will be making ample use of these in future sessions. See you next time.